We just covered with the cricket and temperature example about how to calculate the sum of the squared errors. And so the idea of the least squares regression method is that we are finding the value of the intercept and slope based on minimizing the sum of the squared errors. And so we saw that the sum of the squared errors is exactly what it sounds like. You take all the errors, you square them, and you add them up. And the idea is we want that value to be as small as possible. We want it to be the minimum value because that means that the fitted or predicted values of our outcome and the raw values of our outcome are, in general, they're not all that different. They're pretty close, and we want them to be as close as possible. But the question is, how do we actually find the minimum sum of the squared errors so that we can actually find the value of the intercept and slope? Well, there are really two ways of doing that. You can use calculus, or you can use a visualization technique. Right? You won't have to know the actual calculus behind it, but it is useful to know where the idea behind the sum of the squared errors in terms of minimizing that value. Right? It's important to understand that conceptually. In terms of the calculus, you won't need to know this for this course, and you have to keep in mind that students got degrees from Harvard long before calculus was invented. So Harvard was founded in 1636, and calculus wasn't invented until about 50 years later. So you had generations of students who went to Harvard who didn't know anything about calculus, who they couldn't because it wasn't even invented. So calculus is a very fun and useful way to derive the values of the intercept and slope. But you don't need to know calculus to understand this idea of minimizing the sum of the squared errors. So if you want to use calculus, if you've taken it before, there are a few steps you can do. You can express the sum of the squared errors in terms of the intercept and slope, these values, and then you can take the partial derivatives of the sum of the squared errors with respect to the intercept and slope, and then you can set these partial derivatives equal to 0 because calculus can be used to minimize some function. And so in this case, we're minimizing the sum of the squared errors. And then you can use algebra to solve for the intercept and slope. You do not need to know this. All right, this is just in case if you happen to know calculus, but for this course, you do not need to know this. So the other way to really understand, and I think really the more useful way for most people, is to visualize, because you can minimize the sum of the squared errors using a series of visualization techniques. Conceptually, each squared error or residual, you can visualize it as a box on some set of scatter plot. So suppose you have a small data set of 5 observations, then you'll have 5 errors, 5 residuals, and then accordingly you'll have 5 boxes. And the area for each of those boxes will be equal to the squared error for that particular observation. And then the sum of the squared errors, it's the total area of those boxes. And so you can fit a line to a scatter plot, and you can have this sort of, you can actually visualize to see which line has the, in general, the smallest or the minimum sum of the squared errors. And so you can use this technique to really understand conceptually what's going on with the sum of the squared errors. So suppose we have a data set of 5 observations, and we have this least squares line, right, where y hat equals the intercept plus the slope times x. And the least squares estimates, those values for the intercept or slope, are the intercept of 0.5 and a slope of 1. So then we have this scatter plot here. So we've shown here the least squares estimate, and we have 5 observations, we have 5 errors, and we have 5 squared errors. The squared errors are represented by those boxes. If you add up the area of those boxes, then you will obtain the sum of squared errors. And because for this scatter plot, I've already shown you the least squares line, this is the minimum sum of squared errors for this particular scatter plot. We know that. But suppose we didn't actually know the sum of the squared errors. We didn't know the sum of the squared errors were minimized. We didn't know the least squares regression line. Well, the idea is you can fit multiple lines by changing the value of the intercept and slope, and you can see how those total area of the boxes will get larger and smaller, and you want the total area of those boxes, you want these boxes to be as small as possible overall. So we're going to try out a few lines and see what happens visually to the sum of the squared errors. Because the goal here is to find values of the intercept and slope that make the total area of the boxes as small as possible. We want the sum of the squared errors to be minimized. And so the idea is we can visualize this. And since we already have the least squares regression line, we already know at this moment that the least squares estimate are a value of the intercept of 0.5 and a value of the slope of 1. But it's important to see how we got here by changing the values of the intercept and slope. You'll see when we change the values of the intercept and slope, you'll see that the boxes are going to get larger. Right? The sum of the squared errors for any alternative line than the one shown here, those will have larger values for the sum of the squared errors. So let's talk about finding the intercept and slope. We will try finding our intercept and slope for our line by looking for a line with the smallest possible sum of the squared errors. So first what we're going to do, we're going to see what happens to the sum of the squared errors when we alter values of the intercept while keeping the slope at 1, the least squares estimate that we already know. Next, we're going to see what happens to the sum of squared errors when we alter values of the slope while keeping the intercept, the least squares intercept, the same. Now you can do these simultaneously. You can change the values of the intercept and slope simultaneously, but for the purposes of clarifying what's going on here, it's useful to keep one constant. It's useful to keep the value of the intercept and change the value of the slope, and then keep the value of the slope the same while changing the value of the intercept respectively. So in this case, we have a slope that's the same, but we're just changing the value of the intercept. So here we have an intercept of -1, and we're keeping that slope the same, equal to 1. And you can see that we've just shifted the intercept down from the least squares estimate. You can see the boxes are a little bit larger, right? Here is the least squares value of the intercept, and the boxes shrink a little bit. We're just shifting that line up and down. And then here we have a value of the intercept roughly equal to 2. We've shifted it above, right? So we have these three different values of the intercept. We're keeping the slope the same. And you can see the boxes are a little bit larger. The sum of the squared errors is a little bit larger now. So when we compare these three different lines, okay, we're keeping the slope the same. And we're just changing the possible values of the intercept, the y-intercept. We're changing that value of b naught, b subscript 0. And you can see the boxes get larger and smaller. But we want the sum of the squared errors minimized. We want the total area of those boxes to be as small as possible. So you can see visually, there's out of these three possible candidates, you can change the values of the intercept, but the value of the intercept in which the sum of the squared errors is minimized is actually 0.5. You can see that, okay? Because if we push the intercept down to -1 or push it up to 2, you shift that value of the intercept to any other value but 0.5, and those boxes, the total area of those boxes is going to get a little bit larger, right? So which line has the smallest sum of the squared errors, keeping that slope the same? It's the line with an intercept of a value of 0.5. Right? That's the idea of finding the value of the intercept such that the sum of the squared errors is minimized. Now let's see what happens when we keep the intercept the same and just alter that slope. And what you'll see is if you change that value of the slope to anything other than the least squares estimate, the total area of those boxes will get larger. That's because the least squares estimate is based on finding the minimum sum of the squared errors. So here we're just keeping that intercept the same. Right? We're keeping the intercept at 0.5. And what we're going to do is we're going to change that slope. So in this case, instead of a slope of 1, we have set the slope equal to 0.6. We're just changing that knob. And when you decrease that slope to 0.6, you can see the boxes inflate. The total sum of the squared errors is a little bit larger. Right? Keep in mind, each box represents an error squared. The total area of these boxes is the total sum of the squared errors. If we have the slope equal to 1, the least squares estimate, you can see the total area of those boxes is smaller. Then what happens if we increase the slope to 1.8? You can see the boxes inflate again. We're just keeping the intercept the same and changing the value of that slope. So you can see here which line has the smallest sum of the squared errors. When we keep that intercept the same, we just change the value of the slope, we have, if you change the value of the slope below 1, the boxes inflate. If you change the value of the slope so it's above 1, the boxes inflate. So for this particular scatter plot, the line with the smallest sum of the squared errors results in a slope of 1. Right? By minimizing the sum of the squared errors, we get a slope of 1. And so which line is best out of all of these possible candidates? Well, you can change the value of the intercept and slope. You can fit all these different lines, but the line with the smallest sum of the squared errors, the line with the smallest total area of those boxes, it's a line with an intercept and slope of 0.5 and 1. So when the intercept is 0.5 and the slope is 1, right, that's the line in which the sum of the squared errors is minimized. That is all the calculus is doing. It's using this criterion of finding the total area of the boxes as small as possible and then saying, here's the intercept and slope. When you minimize the sum of the squared errors, you get an intercept and slope with these particular values of 0.5 and 1. Now, a different scatter plot, by minimizing the sum of the squared errors, you're going to get a different intercept and slope value. But the key point is that by minimizing the sum of squared errors, the method of least squares gives you a line that we call the best fit. And conceptually, I think it should be clear why this line is better than those other ones. Because when you have the sum of the squared errors larger, you're just going to have overall more residual, more error. And we want a line that fits the data pretty closely, right? We don't want a big difference between our raw values of our outcome and our fitted values. And so the least squares estimate, it gives us pretty close values between our raw values of our outcome and our fitted values of our outcome. So when we run the least squares method, when we try to find a line by minimizing the sum of the squared errors, by trying all these possible candidates, we obtain an intercept and slope with these particular values. The intercept is 0.5 and the slope is 1. So the least squares method, you can use calculus or visualization, but conceptually, all you really need to know is that by minimizing the sum of squared errors, we get these two particular estimates for the intercept and slope. And the least squares method, as we'll explore in the coming sections, has several nice statistical properties in terms of the residuals, in terms of the values of the intercept and slope, and also in terms of various other properties of our line. And it's those properties that we'll explore in just a moment.